Hey Stat, I think I forgot to tell you that I wasn't going to be here this morning because I'm downtown at an MRI with my son, and I might not be back in time. It's an early appointment, but I still might not get back. So I went ahead and recorded this, so you can be watching it on Wednesday the 5th. So y equals ax to the b we were talking about yesterday, and that's called a power model. And you can take notes on this on your 12.2 handout. So the power model is used when our data is curved. When it's curved, we are sad and our mouth is curved downward because lines are so easy to work with and we can make predictions with them so easily. So I'm going to talk about what to do to straighten this out. So I'm sure you lost all kinds of sleep waiting to see how it's done. Well, it turns out if we know that this is a power relationship, like we talked about yesterday, the area of a pizza given the diameter or the length, the distance that a dropped object falls over time, those are kind of things. And you have a power model. You can put y on, keep y the same, and take x to the power that's involved. I think the two we were looking at yesterday were squared. So in those cases, it would have been x squared. And lo and behold, it creates a straight line. So another way, so this is a second way you can do that, is you can take y, keep it the same, and do a root. And sometimes that will straighten it out. It'll be a different line, but it will still be a straight line. So either one will do, and we'll change our mood altogether. Alright, so let's look at an example. It's always better to do that. So if you look down on your 12.2 handout, we're going to talk about go fish. So it turns out that when they catch fish, they have to weigh them for this tournament, and they flop around so bad they were having trouble getting their weight because they have to be still on the scale, but they could get a better estimate on the length. So they were going to take the length of the fish and try to figure out from that a relationship to the weight. So when they investigated that and they put weight over here, hoping to come up with a linear relationship, they found out that it was curved. So very sad, very sad. So according to our discussion and theory up here, it turned out that the weight could be transformed because length is one dimension and weight will be counting 3 dimensions. Let's just try cubing, going to 3 dimensions and see if there's a relationship between length cubed and weight. So it's a little bit of trial and error to see what works. So sure enough, it turned out straight. And in fact, if you turn over to the next page, there is that flappy mini tab that I gave you yesterday. And from that, you can see where it has length cubed and weight. So when we have that relationship on Minitab, you can grab the coefficients quite easily. And it turns out that for that you would have y equals, what is the coefficient? The constant. I'll do the constant first. The y-intercept, which is their a, plus, and then the slope, 0.04. 0.014, sorry. I gotta grab these quicker. I don't want to use all this video time. 6774 x cubed. So we've cubed what's on the x-axis. So let's put some meaning behind it. So the y-axis was weight equals 4.0, I'll say 7, plus, I'm just going to shorten these, 0.01 1.47 length cubed. All right, so this is a linear relationship now. It has a cube in it, but that's all right. So what else could we do? I talked about the root as well as straightening it out. So let's try that. What if we put length here, length. That's not how it's spelled. When I want to go quick, I can't do it. All right, length on this side, and we're going to cube root the weight. I think up here, on my theory part here, I should have put, I think that this would have been on this axis. So we're going to put some variable here, x, and over here, the cube root. All right, so let's try that. So we're going to do the cube root of weight and the length. So go back and fix that. I wasn't exactly right there. So, and lo and behold, this is also a straight model. So let's go to Minitab for that. It's that flappy part. And you can see it's doing length and cube root of weight. And so let's do y equals, I'm grabbing the constant first, negative 0.02204 plus 0.246616x. So I just do x and y, but then I grab what they really mean. So the y in this case is the cube root of the weight equals negative 0.02204 plus 0.246616, and then when I get to this, it's length. So whatever was on the x-axis, and the y value we have using this to straighten out the data. So sometimes you can use this kind of situation and sometimes this. So how do you know which one is the best, and how do you know when to use which one? All right, well, first let's just use them and see which one's the best. So let's say that the length of the fish is come out to be 36. So say inches. So 36 inches, or would it be centimeters? Let me see what they say. I can't tell what the, centimeters, yeah, 36 inches, pretty long fish. So we're going to say the length is going to be 36 centimeters. So I'm going to ask for a prediction, so we're going to make some inference here, for what the weight would be. So I'm going to use this model and this model. So on the first one, I'm going to say weight equals 4.07 plus 0.0147, length 36 cubed. So when I do that, I get that the weight is 688, around 689 grams. All right, so put that on hold. All right, that's for this model. And now I'm going to try the same example, the same length, 36 centimeters, to see what weight this model will yield. So on this one, I've got the cube root of the weight equals negative 0.022 plus 0.2467. I abbreviated them. And this time I'm putting in the 36 here. So this turns out to be the cube root of the weight equals 8.856. So then I cube both sides, a little math to end our year. Weight equals this number cubed, which is about 695 grams. So a little difference. So which one's the best? Well, one way to tell, and that is on the Minitab itself. And on that Minitab, you will see a quantity that's listed called S. And S we have met before, so let's see if I can point it out to you. So right here, S is a good indicator of which one, even before I try them, which one is going to be better. Because S is the standard deviation of the residuals. In other words, S is the average prediction. That's the average that the prediction will be off. So the average that this predictor will be off is 18 grams, whereas the average that this predictor will be off is only 0.1, what's that number say? 1.12. So obviously you want this model. It's a better one. Check the S. Again, take a note on that. That S is the average prediction, it's the average that the prediction will be off. So you want as lowest possible. All right. So that might, if given raw data and that's all you have, you probably would have a tough time knowing which model to use. And we're going to add to it 2 more models. So just be aware that guess what comes to the rescue? It's the Minitab. The Minitab will tell you what to do because it seems like they've already put it into the Minitab. You can see on these Minitab that they already took and told you that they're using the cube root of the weight. Up here they're telling you that they're using the cube of the length. So let's just trust in our Minitabs. All right, end of part 1.